Okay, so we can start. Welcome back. So last time we finished, for the moment, talking about analysis tools for nonlinear systems. We looked at non-autonomous nonlinear systems. And we said there was a variety of theorems, Lyapunov-like theorems, including actually an invariant set theorem. But we chose to focus on just one simple result. Now, remember the motivation for this was twofold. One, that it was very clear when we proved the Lyapunov results for autonomous systems that we very much relied on the fact that v dot was dependent only on x, okay, and not on time. So we really very much relied on this interplay of geometry and dynamics. And of course, for non-autonomous systems, v dot will be a function of the state and of time. The other aspect, the other motivation, if you want, which we saw, was that even if you just go from linear time invariant systems to linear time varying systems, things get more complicated. For instance, it's not true that if you take a linear time varying system and the eigenvalues of the A matrix are all in the left half plane, then the system tends to zero. That's just not true, and we showed why. We did state the simple result, which we called Barbala's lemma, which said if we consider a function, the dynamic system x dot equal f of x t, we have this result, which is basically just a result in functional analysis, which can be interpreted as a Lyapunov-like result, which says that if you have a lower bounded scalar function v of x, whose derivative is always negative and whose second derivative is bounded, then v dot tends to 0. So remember, in the invariant set theorems for autonomous system, we had that the system tended towards R, the set where v dot equals 0, and then more precisely to the largest invariant set within R. Okay? And in a sense, this kind of stops at the first step, right? We tend towards v dot equals 0. V dot tends to 0. Okay? But it doesn't go any further than that because there's less structure, if you want, in the system. So we made two remarks on this. Okay? The first was that although this is a technical condition, the boundedness of the second derivative, it still has to be verified. And typically, not always, but typically is going to be shown based on the first two properties. Okay? Namely, the way v looks will tell you that v double dot is bounded. And two, of course, that v dot tends to 0 should be your result, so it should be something you're interested in. So typically, v dot will be chosen so that in some way it's minus some error term square or something like this. Okay, so that the fact that d dot tends to 0 implies that the error tends to 0. Any questions about that? Okay. So then we moved on to some ideas about design. And as I said, later on in the course, we'll look more at, more general analysis tools and then their applications in design. So we looked at robust control in the sense discussed in chapter 7. So we said basically we would look at systems described by scalar nth order differential equations. And we said these systems had the particular property that the state x could be written as some scalar x of t and its derivatives up to order n minus 1 we said that this was a particular assumption about this class of systems. And chapter 6 was about how general is this assumption. Okay? So we said, of course, lots of physical systems come in this form because F equal ma, for instance. Okay? And we also said that the difficulty in controlling such systems is that F and B are not exactly known. If F and B were exactly known, we could call this whole right-hand side some V, right? We would have x to the n equal V, we would design V, and at the end we would solve for U, okay? Assuming a measured state, right? So we said what makes this problem interesting and practical is that, of course, F and B are not exactly known. There's going to be some uncertainty depending on the problem at hand. And we gave this example, for instance, where there could be a lot of uncertainty if you deal with, let's say, underwater vehicle dynamics in currents, okay, or robots with large loads. So that's where we were, right? So we said basically we would assume that f of x and t is, of course, unknown, but we have a known estimate. And this, how good this estimate is known as well, okay, or at least the worst case error from this estimate is known, okay. And this, of course, is unknown. And of course, similarly for b of xt, and there's several ways to write that, but basically there's uncertainty on b of xt as well. Okay. So here we are. We have this nth order scalar problem, okay, with uncertainty. We already talked loosely about some versions of it when we talked about second order system with parameters which are known only within certain bounds and how to design stabilizing controllers for these systems. So here we're going to try to be a little more general. And as you will see, this particular set of ideas doesn't directly use Lyapunov theorems for either autonomous or non-autonomous systems. Of course, this is a non-autonomous system. But Lyapunov is very much lurking in the sense that, you know, it's still using scalars that decrease and things like that. And so we said a typical problem we would be interested is to have this system track a desired trajectory. And so the trajectory tracking error will be denoted by x tilde, and is different between the real thing and the desired thing. Okay, so that's where we are. And this whole chapter, and actually many things we're going to do are based on the idea that selecting the right notation, the right variable to look at, is particularly important if you try to solve complex nonlinear problem. And so chapter 6 will have aspects of this, and this is very much in this flavor as well. So what do I mean by this? Well, suppose that your nephew or your daughter, depending on your age, keeps keeps listening to you talking on the phone about homework or whatever, and or on Skype, and she says, you know, you keep talking about feedback. You know, what's feedback? Okay. And so you have this 10-year-old who is asking you that, and so your tendency will probably be, if you're willing to answer her, to answer something like what actually Norbert Wiener said in his book Cybernetics when trying to explain feedback to the lay person. And the explanation is, well, you know, suppose I'm trying to grab this glass, right? If I'm too much to the right, I'll go towards the left, I'll push towards the left, and if too much to the left, I'll push to the right, and I'll end up grabbing the glass. You're completely misleading this child, of course. Okay, this is absolutely not true. As you know very well, you know, if you take a second order, third order equation, right, and you're too much to the left, you push to the right, you don't quite know what's going to happen. It's going to be, it might be oscillations, it might be, you know, diverging things, right? This notion that, you know, if I'm too much to the right, I push to the left, is actually generally true only for first order systems, right? If you have high order systems, you know, it gets a little more complicated for second order, and for third order, who knows, right? So, however, that idea that if I'm too much to the right, I push to the left, you know, using measurements and feedback, right? That is an idea that works for first order systems, and it works even for nonlinear first order systems. Okay, so what we're going to do first is to say, well, we have this nth order problem. We measure the full state. We're going to replace this nth order problem by a basically equivalent first order problem, okay? Because that will have this kind of nice qualitative flavor which will allow us to play with robustness and later on adaptation and so on in much simpler ways. Okay? So the idea here is first, let's replace this nth order problem by a first order problem. So in other words, I would like to create another variable, right? Here the variable of interest is small x, right? That's what I want to follow trajectory x d of t and so on. I would like to create an intermediate variable such that its dynamics is described by a first order differential equation. In other words, here I have to differentiate small x n times to find the control u. I'd like to create a variable such that I have to differentiate it only once to find the control u. Right. And two, I would like, of course, that that variable, controlling this variable solves the original problem of controlling xd to track the trajectory, the x to track the trajectory xd of t. All right? So create an intermediate variable, and we'll call it s. Okay, so be careful, this has nothing to do with the Laplace variable. Okay, and this variable has two properties. One is that its dynamics is a first order dynamics. In other words, it suffices to differentiate S once to find the control law U. All right, so S dot contains U, right? Up there, x to the n contains U, right? Here we'd like that S dot contains U. And we would like that the fact that somehow we control s to 0 as t tends to infinity implies that x tilde of t tends to 0, in other words, when x tends towards x desired. All right? So at this point, we're not solving the control problem. We just say, let's make it first order. All right? So we're looking for an intermediate variable that verifies two properties. Instead of an nth order problem, we have a first order problem. But of course, controlling this variable to 0 solves the original nth order problem. Right? So let's think of it in the case n equal 2, right? So we have x double dot equal f plus bu, right? So what variable could we pick to satisfy the first condition? Well, we could pick v, right? We could pick s equal x dot, right? If we pick s equal x dot, then of course s dot contains u, right? Because s dot is x double dot, right? Now we know that we may want to be a little better than that, because anyway we have a desired trajectory, so we may want to pick x dot minus x d dot, in other words x tilde dot, because that also contains u. Now, of course, the problem is if we do that, the second part doesn't work. Right? If s tends to 0, somehow we manage to make s tend to 0, it will just mean that the velocity tends towards the desired velocity. Right? But not that the position tends towards the desired position. Right? So that doesn't work, okay? Because it's not good enough. Okay. Suppose we wanted to solve the second equation by itself, the second condition by itself. S tends to 0 implies that x tilde tends to 0, okay? Well, of course, we could pick s equal x tilde, right? That would obviously verify that s tends to 0, implies that x tilde tends to 0. But then, of course, the problem, it doesn't verify the first one. Okay? So in other words, we're trying to find an intermediate variable that verifies two conditions that we need to differentiate only once to find the controller, like x dot in the second order system, but also such that if we somehow control it to 0, we have the original condition verified, the original goal achieved, namely that x tilde tends to 0, like picking x tilde directly. Okay. So neither of this works. What we can do is do some kind of a mixture of the two, okay? So let us choose s equal x tilde dot plus x tilde with some scaling factor lambda. So in other words, we're just adding these two guesses, right? And see what happens. So what about the first condition? Well, the first condition is obviously verified, right? Because we have x tilde dot plus something, right? And so x tilde dot contains x dot, which contains, so x tilde dot contains x dot, and therefore if we differentiate it once, right, s dot is equal to x double dot plus a bunch of things. Right? S contains x dot, so s dot contains x double dot, right? And nothing else, of course, cancels it later. So it verifies the first equation, the first condition, that S dot contains U. There's a B floating around, right? No, yeah. Now, I want the second equation to be verified, second condition to be verified. So is it? So you see, S is the sum of the position error and the velocity error, right? So you might say, well, you know, I want the position error to go to 0, right? I don't want the sum of the position and velocity error to go to 0, okay? However, using mathematics considerably beyond the scope of this course, we can write this equation as right? So it's the same equation, of course, right? So, so why am I saying this? Okay, and by the way, we'll make this more formal later on when we talk about virtual systems. So why am I saying this? Because you see that if you now look at this equation, the second equation, it can be interpreted in a completely different way. This second equation can be interpreted as saying I have this variable S. It goes through this low-pass filter. Since I don't use the S variable for Laplace, I just use d over dt. And I get x tilde, right? So in other words, the computer computes this, right? But you can interpret it this way. Namely, you can say, well, this equation of S can be viewed as the equation of a filter where S is the input and x tilde is the output. And then, of course, since you have a stable linear filter, right, if S tends to 0, x tilde will tend to 0 as well. Okay? So, and again, we'll make this second half of the course much more general and much more formal, talking about virtual systems. So, this says this variable actually works because it contains x dot, so we need to differentiate only once to find x double dot and therefore the control input. But because we can interpret this sum as a differential equation driven by S, the fact that S tends to 0 implies that x tilde tends to 0. So it implies the second. So that's the idea. It's a very simple idea, but quite effective. And so, of course, for the general case, n equal, this was n equal 2, right? For the general case n equal n, if I may say, right, we could, for instance, pick S to represent, pick S equals 0 if you want to represent an n-1th order differential equation where all the poles are at the same place. Or generally, we could pick any stable linear equation we want. Okay. So you see, for an nth order system, this reasoning will be exactly the same, right? Namely, we'll have S dot contains d over dt of x to the n-1, right? Because S contains x tilde to the n-1, so S dot contains x to the n, right? And therefore contains u, right? This contains the derivative of x of order n-1. So when you differentiate it, you find the derivative of order n, namely x to the n, and therefore u based on the top equation up there. And of course, it's still true that now we have an n-1 order filter to go from S to x tilde, and therefore if S tends to 0, X tilde tends to 0. Okay? So this shows by picking this intermediate variable S, which in general you can pick this way, for instance, you can replace the original nth order problem by first order problem, and at the same time guarantee that if somehow you manage to solve the first order problem, then you'll have solved the original nth order tracking problem. Okay? So this is, you know, the power of picking this S to itself represent the dynamics. Okay? Now we can see this. So this is what algebra or you know, differential equations tell you. We can see this in a different way geometrically. So suppose we have a second order system with this choice of S. What does, in this plane x dot, what does S equals 0 represent? Okay, so S is x tilde dot plus lambda x tilde. Lambda is, you know, 7 or some positive number. What does S equals 0 represent? How can we draw S equals 0 on this plane? So what is it? Is it a circle, a line, a square? What is it? It's a line, right? So what does it look like? What's the slope? It looks like this, or it looks like that? It looks like this, right? So it has a slope of minus lambda, right? And what else can we say if we want to construct this line? So we have the slope, so we need 1 point. Okay. What's 1 point that belongs to this line? What?
The origin?
No, not the origin actually, but xd, right? So this point xd of t, xd dot of t, right, belongs to this line, right? Because then x tilde and x tilde dot are both 0. Right? So it's a line that moves, right, with the desired trajectory, keeping a constant slope. Okay. And that slope is minus lambda, and it always contains the desired state, xd and xd dot. Okay? Is that fine? Now, let's go to the general nth order case, not just n equal 2, okay? And given my drawing talents, you know, we'll see this s equals 0 from the side. What does it look like? It's a plane, right? It's a hyperplane, right? S equals 0 in Rn, right? In an nth dimensional state is going to be a hyperplane, right? So as I say, if we do it on the side, it's going to look like this, right? And what does it contain? Well, similarly, it contains the desired state, xd of t, the state. Okay? So that's, in the general case, it's a hyperplane, right? In other words, codimension is 1, right? And it contains the desired state. Okay, so that's what it looks like. Okay. Now, suppose that somehow you've made S tend to 0 and stay there, right? So in other words, you've constructed a control law such that this, or more generally this, okay, is an invariant set for a non-autonomous system, namely once you start there, you stay there. Okay. And that you tend towards this invariant set. Okay? So suppose that you've managed to make the system tend to 0 and stay there. Let's even say for, if you want conceptual simplicity, you manage to get it to tend to 0 in some finite time and stay there. Now, geometrically, what does it mean that it stays there? Okay. Well, you see, this S is not anything, right? This S itself corresponds to differential equation. So, for instance, if you manage somehow to make this surface be reached in finite time, and then such that once there, you stay there. Okay, this is still S equals 0, of course. Then what will happen? So you reach infinite time, and somehow you know that once you're in there, you stay there. What happens? Well, once you're in there, of course, you stay along this line. But it means once you're in there, you verify the differential equation x tilde dot plus lambda x tilde equals 0. Right? So once you're in there, you're going to actually slide along this plane all the way to xd. Right? And similarly here, if you reach this, you know, and then you know somehow that once you're there, you stay there, you've made this S equals 0 invariant, then you're going to slide to xd. It might look a little more complicated because it's nth order, right? So the sliding may look like, you know, a spiral or something like that, right? But you will end up at xd, right? So what does it say? What does this say? Is that the algebra, or if you want, or the differential equation analysis says we've replaced a second order problem by a first order problem, or we've replaced an nth order problem by a first order problem. The geometry says S equals 0 is both a place and a dynamics. Right? Is the geometrical interpretation of replacing an nth order problem by a first order problem. S equals 0 is both a place and a dynamics. So if you know that it's invariant, once S equals 0, you stay at 0, then how you move on S equals 0, it's completely defined by S itself. Right? So it's not that you're on this hyperplane and you drift on it or whatever. Because this hyperplane is given by S equals 0, once you're on this hyperplane, you know exactly what happens. There's one trajectory that happens. And that takes you to xd. Right? So introducing this intermediate variable says we replace an nth order problem by a first order problem. The geometric interpretation is that S equals 0 is a hyperplane. But also, because of its definition, it's a dynamics. And therefore, once we know we stay in this hyperplane, on this hyperplane, we know exactly what happens to the trajectory. All right? So replacing an nth order problem by a first order problem also says once you're on this hyperplane, it takes care of itself. Right? Basically, the motion is entirely defined. Okay? Questions about that? All right? Good. So we still haven't solved the control problem, right? The only thing we've done for the moment is we've went from an nth order problem to a first order problem, right? And we've given it this geometric interpretation, right? We can push a little more the analogy, if you want, in terms of going from first order, nth order to first order, by wondering, you know, what if as t tends to infinity, I can only guarantee s less than some constant phi, right? So in other words, we're saying, well, you know, s tends to 0 implies that x tilde tends to 0. Well, so just solve the problem s tends to 0. Now, of course, solving the problem s tend to 0 is itself a control problem, so it may not be solved exactly, right? Instead of having the thing tend to 0, it may tend towards a small region around 0. Okay. So suppose that I know this, somehow I've solved the control problem for s, but I haven't solved it perfectly. I've maintained s within a certain bound. How does this bound on s, this residual error on s, translate as a residual error on my real original problem, which is the problem of controlling xd? All right? And if the answer was, well, you know, there's no clear mapping because it's very, it's very poorly conditioned or whatever, then that would be a problem, right? Because if we would say, well, you know, if s tends to 0.000, this works, and if s tends to a small number, it doesn't. Okay. So here, as we're going to see, it's very nice and smooth. It works very well. So if you have a small error on s, it's going to give you a small error on x tilde. So how do we show this? Well, let's just take first the case n equal 2, right? So we have x equal x tilde dot plus lambda x tilde. We have the structure of a filter. And we know that s is less than phi after transients. Okay, so it's here we have a linear system, so the effective initial conditions, you know, will go away. So we can just look at what happens with arbitrary initial conditions to this system if we give it a function s of t, which is less than phi. Okay. So if you look at this system, this is always true as the definition of S, right? We know that its response, right, is the effect of initial condition in X, right? And then the effect of S. So if we have this input, and actually we did this little calculation last time when we talked about differential inequalities, it's the same calculation, basically. If we have this input, okay, this input is giving us this output x tilde, which is the effective initial condition. This tends to 0, right, because lambda is positive. And then the convolution integral of the impulse response of this filter, right, with S. So sum from 0 to t, x tilde of t. Sum from 0 to t of e to the minus lambda t minus r, s of r dr. Right? So that's what we have, right, if we look at this differential equation. Now, maybe we can pick another color. What can we say about this term? If we look at the absolute, I won't rewrite everything, right? The absolute value of this integral is, of course, less than the integral of the absolute value, right? The absolute value of the sum is less than the sum of the absolute values, right? Now, inside we have the product of this exponential times s of r, right? So the product of the absolute value of the exponential is just the exponential, and the absolute value of s, that's absolute value of s, right? So absolute value of s is less than phi, so we can get this out of the integral. And we have sum from 0 to t of e to the minus lambda t minus r dr. Right? Everybody follows that, right? We have taken the absolute value of this, which is less than the integral of the absolute value. Here we have a product of two terms. One is positive, and the other one will be the absolute value of s. The absolute value of s we can bound by taking out of the integral. We get phi, and then we just left with the integral of this exponential. Okay? And the integral of this exponential, if you can compute it explicitly, right, and you'll find that it's less than phi over lambda, this whole thing. Okay? You have phi times e to the minus lambda t divided by lambda, right? Okay. So, what does it say? It says that we start with some initial conditions. We know they go away. S is always bounded by phi. Then the resulting error, x tilde, will be bounded by phi over lambda. Okay, yes?
Why is the integral s equal to phi?
It's not equal to phi. I've put a bound, right? So you have the integral of the absolute value of this, which is, of course, is the product of the absolute values. The exponential is positive, so you don't have the absolute value doesn't matter, and you have the absolute value of s, right? Now we're trying to upper bound this, so we know that s is less than phi, so we get the phi out of the integral, and what's left is just the exponential, so we just compute the integral. Okay. All right. So that's what it says for second order system. What about an nth order system? Well, we don't need to redo the calculation, right? Because an nth order system is basically here just a sequence of first order systems. So in other words, to go through s from s to x tilde in an nth order system, we go not through one filter, but through n minus 1 filters. So suppose that indeed s is less than phi. How can we bound this term after transients? Well, it would be exactly the same calculation, right? So it would be less than phi over lambda. And so on. So at the end, what do we have? The absolute value of x tilde after transients is less than phi over lambda to the n minus 1, because we have n minus 1 filters. Right? Everybody understands this, right? I'm just saying this is just a sequence of n minus 1 first order filters just like this, right? So the output of the first one is not x tilde, it's something, and then it feeds into a second one, and so on, and there's a total of n minus 1 of them. So instead of having phi over lambda to the power 1, we have phi over lambda to the power n minus 1. Okay. So what it says, therefore, is that if you have a small error, an error on your control of S, then this error can be very explicitly translated into a maximum error on the control of X tilde, and it just scales with the error on S. Right? So you can really go from one problem to the other. It's very easy to show. It's in the book and it's very easy to show. But you can similarly get bounds on the derivatives of X tilde, using phi. So once you have controlled your system S to go to 0, then you automatically have bounds on X tilde dot, and so on, all up to n minus 1. Okay. Questions about that? All right. So all of this, in a sense, is just to step back and say, well, we have this n-order problem. I'm going to try to make the problem simpler for myself. I'm going to first transform it into a first-order problem, and then somehow solve the first-order problem. Okay, so we've delayed this up to now, so now we have to still solve the first-order problem. Okay, but hopefully it should be easier than solving the original nth order from the start. Okay, questions? Okay. So what we'll see is that it's actually very easy to solve this first-order problem because it's a first-order problem. And in a sense, if we are very optimistic and bold, you get a solution which is almost too good to be true. Okay. So we'll see why it's almost too good to be true, and we'll see also why sometimes it is true. Okay. And in the case when it's too good to be true, we'll see how there are ways to change it a little so that it's both realistic and good. So let's look at this. Okay, so let's take a little example. So suppose we just take a second-order system, but really the complexity is the same for an nth-order system because anyway we first always start by replacing the nth order by first order. And so we're going to pick a specific case here just to make it just a little more explicit, but it's just to give you an idea. So this is just a mathematical example, right? So x dot plus a of t, x dot square cosine 3x equal u, with a of t between 1 and 2. All right, so this is your problem. Okay, so for instance, it's not exactly that, but it could be some version of a system where you have some drag term, and the drag term is within a factor of the real thing. This is not that, but you see you would have something very similar. So this is your system. You don't know A, but you know it's between 1 and 2. All right? So what we want to do, right, first of all, is pick an estimate of this dynamics, okay? And this estimate, we would like it to be as close as possible to the real thing, okay? So what's a reasonable choice here? So what's a reasonable choice for x hat? You could choose f hat equals 0 if you want, or f hat equal minus 10. It's your choice, okay? But here I'm saying, how can you choose f hat so that it's a reasonable choice? Well, you could basically pick the value that corresponds to a be in the middle of its two bounds, okay? So it would mean that f hat would be minus, because we put it on the right-hand side, 1.5 x dot square cosine 3x. Okay, so that would be f hat. Now, of course, once you've chosen f hat, you know, here you've put it just in the middle because you don't know a, okay? Once you chosen x hat, of course, you can compute capital F. You have no choice of capital F now, right? Or at least you have no choice of your best estimate of capital F. And so what's that? Well, A was between two values, right? You put it in the middle. Okay, so what's left is what's on either side. Okay, so 0.5 x dot square absolute value of cosine 3x. Right? You've put it in the middle, so what's left is 0.5 on each side. Okay. So, now, so we are in a case like this, right? We have a second order system, so we're in a case like this. And we're going to try to control S, right? So first of all, we're going to compute S dot. Okay, so S, of course, is equal to x tilde dot plus lambda x tilde. S dot is x tilde double dot plus lambda x tilde dot. So x tilde double dot is x double dot, which is f plus bu. There's no b, well, yeah, f plus bu here. Minus x double dot d plus lambda x tilde dot. Okay, so that's the value of f. Okay. All right. So, what would we like S to do? Well, we'd like it to tend to 0. And as I said, you know, we're going to be a little rough at the beginning and then see if we can get away with it. So what we're going to impose is to choose U such that. So what do we want? We want S to always decrease in that absolute value. So we could think of S squared, right? And we would like d over dt of S squared to be negative, right? Which would mean that S would always decrease, okay? But more precisely, we're going to impose something a little stronger, okay? Such that 1/2 of d over dt of S squared be less than minus eta absolute value of S, where eta is some constant, some positive constant. So basically, we want S to decrease in absolute value, but we'll impose how it decreases this way for the moment. Now, what does this imply? Suppose that we start with s equal s positive, right? So remember, we have s equals 0 in this n-dimensional space, right? It's a hyperplane. And of course, this hyperplane divides the space in two half spaces, right? In one half space, we have s positive, and the other half space, we have s negative, right? And it cannot be anything else, right? Because s equals 0 is only on this hyperplane. Okay. So it divides in two half spaces, s positive, s negative. All right. So suppose we start with s positive, right? So we start somewhere here. So we might, end up perhaps there. So how can we write this equation? Well, it's ss dot less than minus eta s, since s is positive. As long as s not equal to 0, we can write this as s dot less than minus eta. And so if you want, it's a little as in the asymptotic proof in Lyapunov theory, right? The derivative of s dot is always less than some finite negative number. Right? So s equals 0 is reached in a finite time, which is inferior to the initial value of s divided by eta for s positive, and you can show it's the same for s negative. Right? So in other words, we start with positive s, so same thing as s dot less than minus 4, right? And therefore, the velocity towards 0 is always finite and negative. So you reach 0 in a time which is less than your initial position divided by eta. All right? So when we impose this condition, in a sense, it's imposing that starting anywhere, we reach s equals 0 in finite time. Okay? Now, what else does this imply? Well, so from here we reach it in finite time, and from there we reach it in finite time, and from here we reach it in finite time, and so on, right? So you see that you start from some initial condition, you reach this hypersurface in finite time, or in the case n equal to this line in finite time. And after that, of course, there's no trajectory going out, right? You've drawn all the trajectories of the system. They tend towards s equals 0. So once you're on the surface, s equals 0, you're trapped. Okay? Once you've reached the surface in finite time, you're trapped. So precisely this surface is an invariant set. Okay? It's a time-varying invariant set. Okay? So once on the surface, you're trapped. So once on the surface, s equals 0. So once on the surface, you know exactly what happens. Namely, you follow this differential equation, s equals 0. Okay? So this is called the sliding condition. And the reason, of course, it's called a sliding condition is that once you reach s equals 0, you slide along the surface with the dynamics given by the equation of the surface itself. Okay. Okay, so let's get back there. Basically, this is what we're trying to do. We're trying to have S verify an equation like this. We're trying to choose the control law so that S verifies an equation like this. Okay. Just for simplicity, let's just pick b equal 1. It doesn't really matter, but just make the algebra a little simpler. So let's define u hat. U hat is the choice of control law that would make S constant if the dynamics was exactly known. All right? So is the choice of control law that would make S equals 0, S dot equals 0, sorry, if we happen to know F, the dynamics F exactly. So what is that? Well, of course, it's simply minus F hat, our best guess of the dynamics, okay, plus x double dot d minus lambda x tilde dot. Right? It's simply the value of the control law that makes this whole right-hand side equal 0 if F hat happens to be exactly equal to F. Right? If we know the dynamics exactly. Okay, it's just a notation. Right, so everybody understands this? So, therefore, by definition of u hat, okay, with u equal u hat, S dot is equal to what? Well, it's simply what we haven't cancelled exactly, right, which is F minus F hat, right? Right, it's just by definition of u hat. Right? U hat is the value of u that would make S dot equal 0 when F hat happens to be equal to F. Right? So we have simply this. Okay? Now, if we compute 1/2 of d over dt of S squared, we get S times S dot, right? So let's compute that. S times S dot, which is 1/2 d over dt of S squared. So if we just apply u equal u hat, then if we compute this quantity, which we would like to be less than minus 3 absolute value of S, well, we see that, that's not good enough. Okay? So we have to do better than that. So let's add something to u, okay? So u equal u hat. And we're going to add a term to u, okay? And the principle is in a sense similar to things we've already seen. In other words, we're going to put a term which is of the right sign, which pushes in the right direction. And remember, we're dealing with first order systems, so we can really play with these, pushing in the right direction. We're going to add a term which is of the correct sign and big enough to overpower this term, which may not be of the correct sign, which in general is a random sign. So in other words, we're going to add to this term minus k sine of S, where sine is the sine function, so it's simply a function which is equal to minus 1 when S is negative, plus 1 when S is positive, and whatever you want when S equals 0, it doesn't really matter. So u hat minus k sine of S. So suppose we do this, okay, what can we say about 1/2 of d over dt of S squared? Well, it's still, of course, equal to SS dot. It's still equal to this term, F minus F hat. But then we have S times k sine of S. So how can we write this? This extra term we've just added, right? We've added a term to u, right? So we've added a term to S dot. So we just get k sine of s times absolute value of s. So how can we write that? Well, it's simply k times absolute value of s, right? Ks times sine of s. Right? S times sine of s is just absolute value of s, right? Okay. So we see now what's going on, right? How can we make this less than minus eta s? We can do this by choosing k equal what? Right? We would like this term to be less than minus eta absolute value of s, okay? So we have this ks term, which is nice, okay? It looks exactly like we want. And then we have this other term. Okay? So this other term is, we don't know its sign, right? But we can bound it. And we can bound it by what? We can bound it by absolute value of s times absolute value of f minus f hat, namely by absolute value of s times capital F. So the only thing we have to do is pick k equal or larger or equal to f plus eta. Right? By choosing k to be equal to eta plus whatever uncertainty we have on f, we guarantee that this equation will always be verified, which will mean that starting anywhere, we reach s equals 0 in finite time and then stay there, meaning that we follow the differential equation defined by s equals 0. All right? So that's what we can do here. And so we can write the corresponding control law, right? It looks complicated, but it's actually very simple because we can see step by step where it comes from. So for the example we had, what would be the control law? Okay, so u is equal to u hat minus k sine of s for this example, x double dot plus a of t x dot square, right? So u hat is minus f hat plus x dot d minus lambda x tilde dot. So if f hat we said was this, right? So 1.5 x dot square cosine 3x plus x double dot d minus lambda x tilde dot. Okay, so that's u hat. Minus k sine of s. Okay, so k is 0.5 x dot square cosine 3x plus eta sine of s, which is x tilde dot plus lambda x tilde. Okay, so this is k. And this is s. Okay, so that's your control law. U equal u hat minus k sine of s. So u hat is minus f hat plus x double dot d minus lambda x tilde dot. So f hat we've replaced by its expression. K is capital F, which is this, plus eta times sine of s. Right? So this control law is what would take your system up there with the a of t, starting anywhere, would make it tend towards s equals 0. And stay there afterwards. Okay. Now, I was saying we get something which is very nice and simple and very robust and almost a little too robust to be true. Okay, so as we'll comment shortly. But so what does it say? It's starting anywhere. And with this uncertainty on f, which we have an explicit bound on, okay, we are going to reach this surface s equals 0 in finite time, and afterwards slide on it with an equation given by the equation of the surface itself. And in particular, suppose, for instance, we start at x equal xd, right? So we give, if you want, the system a feasible trajectory to follow, because a physical system is not going to jump, right? So if you start exactly at x equal xd, what happens? Well, you keep verifying this equation s equals 0 with initial condition 0, so you stay at x equal xd, right? So if you start at x of t equal xd of t, remember xd is a trajectory, right? You keep following this desired trajectory exactly, regardless of the uncertainty outside, right? What does it mean in terms of this diagram, right? You have this surface which keeps moving with xd. You start at x equal xd, so therefore you stay there because that's the only solution of the equation s equals 0, okay? The differential equation s equals 0. While the world is in havoc, right? The world around, this can be a lot of uncertainty, which is going to move all these arrows around. But as far as you are concerned, as long as these arrows keep pointing towards you, towards s equals 0, your motion will be completely insensitive to that. Because your motion will be entirely given by the equation of the surface itself, which doesn't depend on what's happening outside. Okay? So here, we're at a point where we say we have this control which can take an arbitrary amount of uncertainty and do a perfect job. Okay? Particularly if you give it a realistic trajectory, namely a trajectory that starts where you are and then takes you places, then actually you're going to follow it exactly regardless of the uncertainty around, using this control law. So, as I've already mentioned, there's a caveat about that, but it's still, the line of thought is still, standing. We just have to be careful about this last point, okay? So, first of all, this reasoning is actually exactly true for some systems, which we'll explain. And in these systems, you can get incredibly high performance, because precisely you get exactly this kind of behavior, okay? In most systems, though, we'll have to modify things a little to make this realistic. So you'll get very good performance, but at least it will be feasible. Okay? So intuitively, why does this work, and what may be a problem? So if you think again of this diagram, right? So you have this surface here, and you have the arrows moving around. And as long as the arrows move around and keep pointing toward the surface, your motion on the surface is not affected. Okay? So it means, by the way, that they need to be able to move, so they can't start tangent to the surface, right? Because if they move, then they would do this, right? So they need to be like this, pointing towards each other. Which means precisely you need a term like this minus k sine of s, right? A discontinuous term around the surface, right? Which says, on one side of the surface the rise like this, on the other side the rise like that, so to give it some slack. Okay? So the reason it works is that you have this discontinuous control law around the surface, which you see in this k sine of s term. The more slack you want, in other words, the more uncertainty you want to handle, the more discontinuous it's going to be, right? Because it has this capital F term in it. Okay? So if we now take this little drawing, right, or that one, and look at, take a magnifying glass, right? So we have all these arrows, pointing nicely around. And we kind of take a little point here, take a magnifying glass. So now we have the same surface here, s equals 0. And see what happens really, right? So remember, this is a control law, right? So you measure the state, you compute the thing, okay, which of course in today's computer is not going to take very long, even this, right? And you apply the control law for some kind of actuator. Okay? So that's something that takes a little time. Okay? You need to measure the state. Perhaps you have an observer, whatever, which actually, based on the measurements, give you the full state, or you measure the full state. You have a computation, and you have an actuation. Okay? So what it means is that when you really implement this u equal u hat minus k sine of s, you arrive here, and by the time you've done all these little extra computation, you'll have overshot a little. Okay, again, this is kind of a magnifying glass of what happens here. At this point, you have applied the u minus k sine of s, and it starts in the other direction. But the same thing, of course, happens in the other direction. And so on, right? So this happens really fast, and so on average, you're doing exactly what would happen if you didn't have these little overshoots. So if you're on this drawing, this would look like just a little noise, okay? So that wouldn't seem to be a big problem, except that at the level of the control input is chattering back and forth with this full range, right? Here, this little drawing, is just kind of a little noise on this. But if you look at what the control input does, it's banging back and forth in this full range. And of course, generally, it's not good. Not always bad, right? Sometimes you have control inputs which are made to be have large amplitude variations. But sometimes you have control inputs which are made to have large amplitude variations, as in amplitude modulation or things like that. Okay. But in general, you don't want that. Okay. So what's going to happen is that we're going to take this control law, and if we do things like pulse width modulation or pulse frequency modulation, some version of a control law where this chattering is not a problem, then we leave it at that and we get this very nice behavior. Otherwise, what we're going to do is say, well, it's easy enough to kind of fix this. Instead of having this discontinuous control, we're going to try to have some smoother transition. And what we hope to gain from the smooth transition is we'll get rid of the chattering. What we lose is instead of having S tend exactly to 0, it will tend towards some small region around 0. But this is fine because we've just computed before, what happens when S doesn't tend exactly to 0. It tends towards something like phi. Okay. So that will be the plan next time. We'll see first that, if your system can handle this, then you can implement this directly and you have very high performance controllers. 2, for most systems, it's not going to be the case. But you can easily smooth this, make this less brutal, if you want. What you'll gain from this is that you'll get rid of this controlled chattering. What you'll lose from it, instead of having this kind of perfect, almost miraculous tracking error, you'll have some small tracking error. Okay. Yes?
Kind of sensitive to modeling errors, like because the U depends on your original second order model.
Yeah. Yes.
So how robust is it to modeling errors?
So the question is which modeling errors, right? So that's a very good question. So these modeling errors is very robust by construction. What I've just said about why we don't want in general chattering is that there's going to be other errors, namely unmodeled, presumably fast dynamics. Okay? And those are the ones which don't play with chattering. Okay? And so that's where we're going to be able to play.